السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Do you have any questions on the first part? So what do you mean by embeddings? First, is it a vector? It is a vector representation, right? Okay, is it latent or observed? Latent, right? Which means that it is dense and it is, a less number of dimensions, okay? And it captures the semantics of the term, okay? Type. We discussed one way of doing embeddings, which is an old way, which is latent semantic analysis. Then, inshallah, we'll turn to newer methods. We'll try to be as simple as possible, just giving you the basic concepts behind these methods. One of the very famous methods of embeddings called word-to-vec, and from the name, it tries, as we saw before, to convert from a word to a vector. Okay, that's why it's called word-to-vec. So the goal is to use, as we will see, very shallow neural network, to learn the meaning of words from very large collection of text in an unsupervised way. So we don't need any labelings, any annotations. We don't need to do anything. Just by raw text, I can use this method or these methods to learn embeddings for words in the collection. How we do that? Word2Vec has two architectures. One is called skipgram, and the other is called continuous bag of words. We'll discuss each. But what is common between them is that we define a context window, okay, and it is fixed size. Let's say 5, okay? So we have a word in the middle and 2 words before and 2 words after. Okay, so that's the window. Let's assume that this is, for example, the window that we will use. And you will see that we will use this window in a bit different way between skipgram and continuous bag of words. But the main idea is we will have access to a very large collection of text, maybe millions of documents or billions of documents, unsupervised. There is no labels, there's no annotations at all. We will just move this window, context window, across the entire collection, okay? And that will provide for us, as you will see, will provide for us the examples that we will use for training the model, Ya Ahlam and Khawla. Okay? So you will see how we can use these windows to generate training examples that the neural model can learn from to get the embeddings. So the first one is skipgram. The idea of skipgram is to train a model that will predict a term given one of its neighbors. Regardless of now, let's put aside what or how the model is actually learned. But the goal here in that model is, given one word, I want to predict a term that appears in the neighborhood of that first term. Okay. So, for example, let's say that I have Qatar University is open is closed. No, let's say let's keep it open. Open in the summer. Okay? And let's say that the context window is 5 words. Okay. طيب, for neural models or any learning model, any supervised learning model, we need to provide training data. Okay, we need to say here's the input, and here's this is what output we need to get if we are given that input. Okay, so from this example, you will see how we will generate the training data for the model to learn from. So the context window, we said that it's 5, right? So this is the 5 words. We'll take the middle one, which is, okay? Forget about stop words now, okay? Let's assume that all of them are not stop words, we are not removing stop words. So is will be the input, and each of these 4 words will be the output, because now the task that I want to learn is, given one word in a context, predict another word in the same context. Okay, give me another word in the same context. Or in other words, learn the embeddings that will make these 2 words similar, because they appear in similar contexts, right? So here it will be is, and what will be the output, the predicted value? Not Qatar University. It's just one word at a time. So is and Qatar, that's one training example. Is and university, is and open, is and in. Okay? What else? Yes, we will move the window now. We'll have another window. So the middle now will be open. So it will be open and university, open and is, open and in, open and the, and so on. Okay? So you see now how we can generate the training data, which looks like supervised, right? It looks like labeled, but the label are automatic, okay, automated. The generation of the labels are automated, right? So this is called, by the way, self-supervised. This method of learning is called self-supervised. The model itself that we will use is supervised, so there must be labels. But we generated the labels this way, which is automated. We didn't need even to have humans go and label them. So we will now feed this training data to the learning model. And it happened here that the learning model is a neural network of 2 layers. Okay? The neural network has the notion of layers, and usually there is an input layer, and there must be an output layer, and at least we have at least the input and the output, and we might have any other layers in between. We call them hidden layers. Okay, so for skipgram, we have just one hidden layer, which is this one. So that's the hidden layer. And between each of these layers, there are connections, and these connections are represented by a weight matrix. Okay, so this is the weight matrix between the input layer and the hidden layer. We call it here W in, W input, and the weight matrix between the hidden layer and the output layer is called here W out. Okay, and the computations are done this way. We multiply the input vector with the W in, and then the result is multiplied by the W out to get the output. Okay, we call this the forward pass. Okay, now there is a way to learn these weights. These weights are the parameters of the model. These are actually the weights that we want to learn. These are actually the embeddings, as you will see. Okay, so we want to learn these weights such that the model will learn, given one word, it will learn to predict, to get the vector representation of another word in the neighborhood. Okay, and to force the network to learn that these two words have to have similar representations, we have what we call a loss function, and this loss function, it's an optimization problem. We want to optimize it. We want to minimize it. Okay, and by minimizing it, we will force the network to learn embeddings or vectors for the words that appear in the same context to be similar, to be close to each other. Okay, so that's the main idea. We'll talk about some details, but this is the main picture. Yes? Related. It is related. Yes. Okay. So here we predict a term given one of its neighbors, and this is called, the architecture is called skipgram. Okay. Any question on that? Yes. Okay. We talked about that already, right? The labels for the supervised learning, the input and the output, right? The output is the label. Here, what is the output? What do we want to predict? Again, for the first context, is and Qatar is a pair, input and output. So Qatar is like a label for is in that example. And university is a label for is, and the open is a label for is, and so on. So every pair, in this way, is a training example, input and output. Okay. The first term is input, and the second term is output. Okay, now, how do we represent the input, actually? The input has to be a vector, right? So, how do we get this vector? Right. We said that the input is a term and the output is a term, right? Of course, the neural network is a mathematical model. Okay, so we have to deal with numbers. We cannot just give is and we get cut out of the model, right? We have to get a mathematical representation. We give the mathematical representation of is, and we get the mathematical representation of Qatar. Okay, in this case, the input and output are observed representation, or actually in skipgram it's just one hot encoding, the local representation. Okay, so this vector is really long. Okay, it's just the vocabulary size, and this is just one, which is 1, and the other are zeros. And the output is similar. Okay, so I want the input is representing is, for example, for the first example, and also it would be one hot encoding for the output. Where are the embeddings? We will see them in the next slide. Okay, the embeddings are actually the weight matrices that you will see here. Okay, so let me summarize again what we said. We will generate training data to feed, to learn a model. That model will learn, given a word, it will learn to predict, or to provide that. Predict means it will give me as an output one word that is in the neighborhood of the input word. Okay? To learn that, we have a neural network of, actually this is called two-layer neural network, because we have two matrices, two weight matrices, but we have input, output, and the hidden layer. And what we will learn actually is the weight matrices type. When we learn, or in order to learn the weight matrices, we have to learn based on some criteria, right? The criteria will be what you will see in this slide, which we call the loss function. The loss function is the function that we optimize, and when we optimize, we get the weights or the parameters of the model that will optimize that function. Okay, so we put a function. This function represent an optimization problem. Optimization means minimization or maximization, right? Usually here it's minimization because we want to minimize the loss, we want to minimize the error. Okay? Type. To minimize the error, we want to get the weights that will give us that minimum error. And this is what we will learn actually in the model. So we will learn, the network will start to change or to update or to learn weights so that the loss will be the minimum possible. Of course, we will not cover how the learning is done. This is in machine learning course. It's done using what we call backpropagation. Okay, but we will not cover it here. But just for you to understand that we will learn that these weights based on minimizing or for the goal of minimizing the given function, the given loss function. Now, let's understand as much as we can the loss function. If you look at this loss function, it's, forget about this minus now, it's 1 over S. What is S? S is all the windows over the training data. Okay, we defined this window, right? So all possible windows in the training data, that's the number of all contexts, which is S. So 1 over all the contexts. Okay. Now, this is for each context. We will, now remember for each context we get the middle word, right? We focus on the middle word and we try with all the words that is in the neighborhood. This is now summation over all the contexts. Now for one context, which is context number I, we go over all the words in the neighborhood of Ti. Ti is the middle word. Okay, so Ti is the middle word. And Ti plus J is the word in the neighborhood. And J goes from minus C to plus C. Okay, minus, and this is this is the size of the window, left and right. Okay, right. Now, for each pair, for each neighboring term, I want to get what I will get from the network is this probability. Okay, so this is the probability that I will get Ti plus J, which is the actual word that I want to predict given the input. Now, the best I can do is that the probability to get this word given this output word, given this input word is 1, right? That's the best, the perfect. In the perfect case, if the network is perfect, given Ti, it will give me Ti plus J, right? With probability 1. In that case, log 1 is 0. Okay, and if that's done in all cases, then the loss is 0, which is the minimum possible. Okay, so that shows you that, yeah, Marina, if we, Marina, are you with us? Okay. If we get perfect predictions, then this loss function is really minimized. That's the minimum. Okay, fine. How we could compute this probability? Now, of course, if there is any error, this probability will not be 1. It might be less, a bit less than 1, or maybe much less. Maybe 0.1 or maybe 0. Okay? If that's the case, then the loss will be higher than 0. And that's what we want to minimize. Okay? Fine. This probability is computed that way. So this is what we want to, as a whole, this is what we want to minimize. Now, let's see what is this probability or how it is computed. Now, let's look at, so this is exponential of something over the summation of other exponentials. So let's focus on this part. Let's focus on this part. What is this part? This is W out. What is W out? That's the matrix at the output layer, multiplied by the vector of the output. Okay. This is actually what we call the embeddings of the output vector. Now let's look at this in terms of numbers. Let's assume that we have here 10,000 words in the vocabulary. Okay, so this vector is 10,000 by 1, right? Right. This matrix, and let's say that the hidden layer, actually the size of the hidden layer is the size of the embedding space that we want. So we control it. Okay, let's say that I want the size to be 200. So I will have 200 here, which means that this is 200 by 1, right? To get 200 by 1 here from 10,000 by 1, then what should be the dimensions of this matrix? Okay, it's actually the opposite multiplication, by the way. It's Wn times the vector. Okay? Or this vector transpose times this. So let's say that this vector transpose times this. So this vector transpose is 1 by 10,000. That's Ti transpose. Now times Wn will give us a vector of size 1 by 200, which is the transpose of it. Okay, so if you remember, this has to be 10,000 by 200. Okay, so that's the size of this matrix. Now, the size of that matrix is similar. What is the dimensions here? What are the number of dimensions here? 200 or 10,000? 10,000. Okay, remember the input and the output are one hot representation. So that's the original local representation. So that will be again 10,000 by 1. Okay, and this will be 200 by 10,000. So this is 10,000 by 200. Okay, right. Now let's see W. We said W out times VTIJ. So W out is 210,000 and Tij is 10,000 by 1. So if we multiply these two vectors, what will we get in terms of size? 200 by 1. Okay. Right. Let's think about this. We have a matrix which is 200 by 10,000. So something like this, right? Right? Multiplied by vector which is 10,000 by 1. Okay, right. This vector is one hot, right? Which means that there is only one here and the others are zeros. Okay, let's say that this one is at dimension 50. Not 50, actually, relative to this, it cannot be 50. Let's say 9,500. Okay? If you multiply this matrix by this, what will we get? Which is what? I know it's in the which is what? No. What exactly from this matrix? What exactly will be the output? if you multiply this matrix by this vector that has only one and the others are zeros. Just what? How do we multiply matrix by a vector? So the first element, let's say that this is the, okay, let me change this. So that's, what would be the first element here? First, what is the size here? 200 by 1, right? Okay. No. That's 200 by 1. Okay. What is the first element here? How do we compute it? How do we compute it? We multiply this row by this, right? What will we get? Just what? We know that this is 9,500. Yes, the value in the column 9,500 will be this, right? Right? Okay. How about the second one? Same, and what do you mean by same? Yeah, the one in 9,500 next row. And then this one, right? And then this one, right? And so on. So what will we get? Column number. Oh, that's not a column. Bit better. So that's column number 9,500. This is the output, the out embedding of term Tij. Okay? So that means that the embeddings are actually the columns of the weight matrix. Similarly, it's very similar to Wn. Okay? So, but here it will be a row, actually, not a column, probably. Okay. So did you get the idea here? So the matrix, there are two embeddings actually. There is in embeddings and out embeddings, and they are actually the rows and columns of these matrices. Okay. So once we learn these matrices, getting the embeddings are just the rows and columns of these matrices. Just lookup table. Okay? Right. Let's get back to the equation here. So we said that this is the out embeddings of the. So that's what we want to get eventually for term Tij, Ti plus j. Okay? And this is similarly is the in embeddings for term Ti. Okay, are you with me? Is that clear? Yes or no? Yes? Kind of. How much similarity is this? 0.0, mashallah. 0.0 means kind of. يعني عشان ما تزعلنيش يعني. Okay. طب ليه يا مريم؟ Did you understand this? You understood this, right? Huh? Did you understand this? Okay. This one you understood, right? Okay. When we multiply. It's not a simple situation, it's always. It will be always, right? Because here the output is always one hot. Okay? So when we multiply it by this matrix, we will get the column corresponding to this one. Yes. So we'll get this one, which we call it the out embedding of ti plus j. Okay. Now the in embedding for ti is by multiplying wn by this vector, as you see here, wn by this vector, which sorry, by this vector, not this vector. This vector, this is the input vector. Okay. Now it's similar, right? We have also here only one non-zero. Okay. So when we do that, let's try to do that. Actually, this is wrong, by the way. This should be 200 times 200 by 10,000. Yeah, there is some transpose here. Okay, let me see. Wn with VTI. So VTI is 1,000. Oh yes, so that should be 200. So it's just the opposite. Okay. So that's 200. That's 200 by 10,000. And this one is the opposite. Which is 10,000 by 200. Okay. And what we said here is actually applies here. Okay. Which is Wn times the input vector. So whatever this value, let's say that this is at dimension 30, then this will be the column number 30 in Wn. That's the embedding that we learned for term that has one at dimension 30. Okay? Mayam? Yes. Yes. Huh? Okay, good question. Okay, the input and output is sparse. Input and output actually are one hot, but that's not the embeddings that we want to learn. The input and the output we don't learn the input and the output here. We want to learn the weight matrices so that if I give that input, I get that output. Okay, and these matrices will be the embeddings as we saw. Okay, now if you think about this now, so this is the embedding for Ti and this is the embedding for Tij. Okay, when we multiply, this is a vector. Okay, this is a vector and multiply by that vector. Does that remind you of something? When we multiply two vectors, what does that mean? If they are normalized, what does that mean? That's similarity. Okay, that's kind of cosine similarity. Okay, type. So this is, we can think of it as the similarity between these two terms. But in what space? In the local space? In the embedding space. In the embedding space. This is what we want to learn. Okay? So that's the similarity between the input representation, the representation of the input word in the embedding space, and the representation of the output word in the embedding space. That's what we want to learn. And we want to maximize actually, so that this probability will be 1. We want to learn these weights so that this probability will be 1. Actually, this is the numerator, exponential of the similarity, over the exponential of the similarity between Ti and all other words in the collection. Okay, so this is the probability of getting Ti plus j given Ti. Okay, normalizing by all the similarities between Ti and every other term in the vocabulary. We want to maximize this, which means we want to maximize the numerator, because the numerator actually is like constant, just for normalization. So we want to maximize this. When we maximize this, which means that maximizing the similarity, which means that we want these two to be as similar as possible when we learn that model. Which minimizing the loss means maximizing this similarity. Exactly. Okay? So eventually, what we will learn using all of these training examples, of course, we have so many training examples, right? If we have very large collection, then we have so many training examples, then we will learn eventually embeddings that will push the vectors of words that appear in the same context to be very similar, which means very close to each other in the embedding space. Is that clear?
Doctor?
Yes, Muhammad.
So, can you help me understand what EXP is supposed to mean? 'Cause I'm
Exponential.
assuming it's not.
Yeah, sorry.
So we're basing it.
EXP means exponential. Exponential of x. This is x.
Then what? But for taking the log, doesn't that just means we're eliminating the log?
A good point.
Sorry, but,
No. Exponent. When we do this, we are normalizing the values, so it will be between 0 and 1. Yani, this value will always be between 0 and 1.
I see. Thank you.
So we can use it, we can look at it as a probability, and when we take the log, then if this is 1, we get 0. The numerator is 1, of course, perfect value. If both have the same, but do we need that? Do we want that? Do we want two terms? Sometimes, right? But sometimes we don't need the terms to have exactly the same embedding. Okay, but similar. This is a very big optimization problem, right? We want to optimize with so many variables. And imagine here, how many variables we have? Can you tell me how many parameters we have in this model? What do you mean by how many parameters we have? How many parameters that we learn? The weights, exactly. Yes, Tuba? Times 2, exactly. Okay, of course, this is very small example, right? We are assuming that we have only 10,000 terms. In reality, we have millions of terms. Okay, so it's a very big optimization problem, but of course, the solution is iterative. Okay, we don't care about how we learn these weights, but this is the idea. We want to learn these weights so that we minimize this loss function. Yes. Yes. Fine. We'll generate all the training data and let the network learn from them. Yes. Actually, the same pair can repeat. And that's okay. Can repeat, of course. Yes, the same pair can repeat, and we have same different output for the same input. Yes. And this is clear from this example even, right? Because we have is as input and qadar as output. Is as input and university as output. Okay? Okay? That's not a problem. Maybe in classification is a problem, but that's that you need to change your way of thinking. That's not a classification problem. Yes. I saw hands. Okay. So is it clear? Should we have a quiz now? Should we have a quiz now? Sudden quiz. Sudden death. Maybe a question, not a quiz. Okay, and should I ask you a question, Annie? Quiz with answer. Did you find the quiz with answer before? يعني both, يعني quiz and answer? In your dream, maybe? Okay. I don't have a question in mind, but please ask me if you have any questions. Huh? By mistake? Oh. Which one? Ah, the dream came to be true. Really? Which one? Which one? In this context? In this one? طيب anyway يعني خلاص. Then this is removed from the. Huh? The by tracking? Eye tracking. Ah. I will replace it, man. I will replace it, man. طيب anyway. This is typical mistakes of. Huh? He will kill you, yeah. I don't think you should leave this class. Okay. Any questions? طيب, I think we should move on now. طيب, we said that there are two models, right, in Word2Vec. By the way, Word2Vec is a library that you can use, and you provide the term, it gives you the embeddings, because it's pre-trained, right? And that can be trained once on a very large collection or maybe set of collections, and then you get these embeddings given a word. You can actually specify if you want skip gram or a continuous bag of words. What do you mean by continuous bag of words? Very similar to the previous one, but here we want to predict the middle term given a bag of all neighboring terms. Okay, so the input here is not just the representation of one word, it's the representation of all words within the window. So if we get back to our example here, then the first training example will be is with all Qatar University open in together. How do we get them together? We just add their one hot representation, which means that we'll have just 4 ones in the input, right? Because each of these is one hot. When we add them, then we just get 4 ones, and that will be the input now. That's the only difference between skip gram and the continuous bag of words. Here we have bag of words because we represent directly the entire context. It's not just word by word, it's just the entire context is given as input, and we want to predict the middle word. Yes? You raised your hand, right? خلاص؟ Okay, الحمد لله. Will be what? Including the middle one? No. Excluding the middle one. The whole context excluding the middle one. That's the input, and the output is the middle one. Why are you confused? Where is the confusion? Opposite of what? No. No. Okay, sorry. Okay. Okay. Now, okay. This is symmetric, right? Now, that's symmetric. This one is not. So we are given the entire context, and we want to predict the middle term. Okay? Are you still confused? Why? What's your question? Yeah, sure. Okay. So A, B, C, D, E, F, G. These are words, okay, terms. How can we generate training examples here? Let's say that the context is still 5. So that's the first context. Where is the middle word? C. Okay, so what will be the input? A plus B plus D plus E. And the output will be C. Then we switch to the next window. What will be the training example here? B plus C plus E plus F, and the output will be D. Okay. Same thing, exactly the same thing. You see that it's the same network. We have W in and W out, and also we learn about. By the way, I forgot to say that in both skipgram and the continuous back of words, we have two embeddings, right? One from the W out and one from W in. Usually we ignore one of them. We don't need both. Okay, so we use either W in and or W out. Usually it is W in. Okay, but we have both. Actually, some retrieval models that we will not, I think, cover use both. Okay, but usually we just use one of them. Huh? For the embeddings. Remember, we said that for one term, each column here is an embedding for a term, right? So all of these columns are the embeddings for terms. And we have also here, but this is different. So this is like different set of embeddings. Okay? So we can either use this or that. Okay? Who is talking? Yes. Okay. What do you think? Do we have these weights before training or not? No, why not? Yes. So that's actually what we train. We train the model by learning these numbers or these weights. Okay? Is that clear now? Okay. After let's say that we have a black box called training. Okay, we will feed that black box all of the training data that we will generate from the collection. Okay, we all understand that, right? Okay. Out of that box, we will get the embeddings, which is one of these matrices. Let's say the input matrix. Okay, and feed all of this training data to that box. After some time, which is not small, by the way, and it's not minutes, it's maybe hours or days, maybe. Okay, and we will get that embeddings, which is a huge matrix, as we said, right? If we have millions of terms, that's huge matrix. These are the embeddings. Now, this is the learning is done. Alas, we learned embeddings for the terms in a new space. Now we can use these embeddings in whatever task we want to use it for. Okay. Now, inside that box is that architecture, and this is the neural network. It learns from all of these examples to know which weights will minimize the loss function. And then after going through these examples maybe multiple times, it will output the matrix that is the goal of all of this thing, which is the embeddings. Is that clear now? So answering your question, this matrix is just for one term or for everything? For all terms, yes, exactly. Each column is the embeddings for one term. What do you mean by the ratio? Yes, now the output will be that matrix, which is, we said 200, right? By 10,000 for in our examples. So this is something like this. Each column here. Now let's say that this is. Let's say that this is a column. This is a vector, Mariam. It's a dense vector. Okay, I will show you an example now. Okay, so here's an example. Let's say that this is for Qatar. Okay, Qatar is number 9,000. Okay, the one hot representation of it is a vector of all zeros except one in the dimension of 9,000. Okay, so column number 9,000 here is the embedding for the word Qatar. Now what is in that column? Can be something like numbers. It's like 0.1, 0.03, 0.27, and so on. It's dense. All of these are mostly non-zeros. It is. How did we get these numbers? From minimizing the loss function that we saw in the previous slide. It's a long story. The minimization is a long story. We will not get into it. Just imagine that we feed this to an optimizer and a code that will, a system that will learn and will give us back this. After the black box, will give us back this matrix. Yes, of course. Yes. And black box actually has the equation already built in, and it will learn. If you are training new embeddings, but embeddings are already pre-trained, they are available already, you can use them. And for English, for example, there are word-to-vec embeddings. You can use them directly. You don't need to retrain because it was trained on huge data sets. You don't need to retrain them. Yes, you can use them, of course. Yes, they are available. Yes, these are called pre-trained embeddings. They are trained already. You can use, actually there are, I think, multiple dimensions. There's one trained, I think, for 300, one for 400, one for 500 dimensions. Okay, so the length of the vector, of course, as we add more vectors, will that be better logically or not? It should be better, right? Because it's larger representation, right? It learns more. Okay? Contain more information. Yes. Okay? But of course, shorter is more efficient. Ask me more questions. I want to make sure that you understand this. Where is 0.9? What is that? What is that number? Yes. Yeah. Which is which, Yani? What is the level? I don't understand. Where is the level here? We are not using any threshold here. You are talking about something like threshold, right? I don't get what you mean. If you are talking about which column belongs to Qatar and which column belongs to university, that's another question. Is that your question? Each row represents one dimension of the embedding space, which is not interpretable. And I cannot say now, remember the features when we talked about the observed representation, right? The 200 here are the features, but we don't know the meaning of them. And I cannot tell you that the first feature, this is the flies -3, as we said before. in the observed evidence. No, we don't know the meaning of each one, but it is a dense representation. The whole thing is a dense representation for that term. Okay. Now the hope is, or what we train the network for, is that if two terms are semantically similar, يا طيبة, then the representation of them should be closer in that space. And if I compute the cosine similarity between them, it shouldn't be that small. Actually, what the goal here is, if and one of the usage here is that I can, because now I have this representation for each term, right? I can look up the most similar words to the word teaching. How? Exactly. Take the top. Hopefully that will be like learning, instructor, university. These are the words that should be the most similar to the word teaching, because they occur in the context a lot. That's what we are capturing by these tests, whether it is skip graph or continuous back and forth. Is it clear now, Maya? Any other confusions? Yes, we will finish this session today. Okay? Yes. Not more columns, more rows here. More columns means more terms. More rows means more dimensions. Yes, because more dimensions means I'm capturing more information. Yeah. The extreme is to use very large space, which we started with, right? So the goal here is to get a compact representation. Okay? Marina. Should I go with everyone? Bashir. والله يا راجل أكيد يعني قول والله طيب okay طيب we can move on. This is the loss function, very similar to the previous one. This is for the continuous back and forth, very similar to the previous one, except that we sum the so that's the input. That's actually the so that's the input in this case, which is the sum of the vectors of the words that appear in the neighborhood. There is another. I'm not sure if this is neural. Huh? Sorry. Don't worry about the equation here. It's what I'm saying here is that this is another method. It's very similar in principle to the word to vec. Okay, but the main difference is in the loss function. Okay, the loss function here uses the squared error, the error between the number of times two words appear minus the predicted probability. So this is the actual co-occurrence probability. What is the probability? Actually, if I look at the entire collection, I can compute the probability of co-occurrence between two terms, right? The actual probability. And this is the predicted probability. Okay? So the loss function here compares between these two. That's the whole thing, the whole idea. I don't want you to know more than that. Okay? But it will learn different embeddings. Okay? So changing the loss function, of course, will give us different learned weights. Okay? And thus different embeddings. So this is called global, I think, global something, vector embeddings, something like This is also one of the well-known, and it is available for English. I'm talking about English here. Okay, so Word2Vec is available already, pre-trained. You can use it. Glove also is available, and both are used for a long time. Yes. What do you mean by the same? Same embeddings? Of course not. Embeddings will be different. No, I think Glove is I will check, but I think Glove is not newer, if I remember correctly. Okay. Did I answer your question or? The output is the output of the training, you mean, or the output of what? Okay. Well, that's what I don't remember. I don't think it's newer I don't think it's newer, if I remember correctly. Okay. I will check and let you know next time, but if I remember correctly, it's not newer. Okay, and this is what's called saturation function. It I think there is an example here. It truncate the expected value. Don't worry about it. One point here that is different from Word2Vec. As Word2Vec, also it has two in and out embeddings, but here the sum of both is the embeddings for each term. They chose it that way. I don't remember why, but the embeddings here, in Word2Vec we said that we have two embeddings. We usually use one of them only. Here both of them are used by just the sum. Okay, it's like capturing both ways of embeddings. Any questions about this? So what I wanted you to know about this, I think, is maybe two things. First, that the loss function is different. Okay. Here we compare, or we get the error between the actual co-occurrence probability and predicted, and the other one is that the final embeddings is the sum of the in and out embeddings. What? So it's a neural. No, loss function doesn't mean that it is neural. I don't want to say something that I'm not very confident in, so I will check and let you know. Okay, this is an extension. After Word2Vec, researchers thought about paragraph to Vec. Okay, which means let's represent paragraphs as vectors. So let's learn vector. Sorry. Let's learn vectors. Let's learn vectors for paragraphs instead of learning vectors for terms. Okay. So the idea is very simple. Don't look at this part. Okay. Look at only the top part. Remember, in skipgram, the input was one term and the output was the one term in the neighborhood, right? Here, the input is a document or a paragraph, and the output is a term in that document. So I will take all documents or all paragraphs, whatever, we call it document here. Whether the document is actual document or paragraphs, it's similar. We take all documents, and the training data will be as follows. Document and each of the terms as an example. Okay, so let's say that the document has 10 words. So out of this document, I will generate 10 training examples. The document and each of these terms. Right. In skipgram, we said that the input and output is one hot encoding, right? Here it's also one hot. Documents and terms. One hot for each document. But here the dimensions of documents are the documents. Okay, and let's say that we have 500 documents in our collection, then the dimension of the document vector will be 500, with only one and the rest is zeros, and the output is the one hot for terms, not for documents. Okay, is that clear? That will be two examples. So the idea here is that we want to get a representation for the document that captures the representations of the terms. Okay? Yes, because the representation of the document is more about the topic. What do you mean? Yes. 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 It's not two terms here. We are not learning embeddings for terms here. We are learning embeddings for documents. Yes, so this matrix now will have a dimension for documents. Okay, so this is the embeddings for the documents that we will learn. Okay, if you want to look at it similar to what we did in skipgram and in Word2Vec, then now we're talking about similarity of two documents. Columns in this matrix, yes, will be embeddings for documents. Yes, but let me emphasize one thing here. When we say I want the input document and the output is a term, and we change the term with every occurrence of a term in that document, that means that I want to learn embeddings for that document that is close to each of these terms. Right? The network now gets training to get the document to be closer to the term, right? Right? If I repeat that for every term in the document, then I want a representation to the document that will be similar as much as possible to all terms in the document. Okay, so it's like capturing all the semantics of all terms in that document. Okay, so this is what we call paragraph to vec. Optionally, we can also do what we do in skipgram, in continuous bag of words. If you look at this rotated, this is exactly what we had in the input part. Khawla and Ahlam, please separate. I understand. If you look at this bottom part, rotated, this is the input half of continuous bag of words. So we can also do that. And the output is here will be concatenated with this hidden layer. So that's another option in paragraph 2vec. So here it will have training data like continuous bag of words plus the training data that we mentioned for the document and terms. All of them are fed to the training box. Right. The main idea here is to learn not representation for a term or for terms, it's representation for documents. Okay, for full documents or paragraphs or whatever the unit that we are talking about. Yes, here I predict one term that appeared in that document. And of course, I will repeat that for every term. So the network get to train from associating all or every term in the document to that document. Okay? And this is, all of this, by the way, is done offline or online? Offline, of course, right? We have already the data, and it's self-supervised, right? We don't need to do any labeling. Yes?
Why we need to paragraph to vector? Because we have already different or designing this similarity between two documents. So here is the same idea.
Okay. You mean the when we talked about how we can represent document given the embeddings of a term, right? Of terms. We said that we can average or sum, right? Yes, that's a good question. So the question is, we earlier mentioned that we can get a representation for a document given the representation of the terms. Embeddings for a document given the embeddings of terms, right? And straightforward way is to sum them or average them, right? Why do we have? Why do we need another method? Who said that the optimal way or the best way of representing or getting the embeddings of a document is to do that? Is to do the average or to get the sum? Maybe there is another way. So here we are learning it from scratch. Okay, it's a different way of representing the document. The first one is not the optimal. Yes. Okay, we mentioned that, but it seems like it was not clear. Any answer? Do you mean what is the representation of the input here? Any answer? Okay. Again, this is one hot encoding for documents. So if I have in the collection 50,000 documents, and I'm talking about here document number 100, so this will be a vector of 50,000 dimension, but only one at 100. It's one hot encoding in the local space of documents. Did you understand the one hot encoding for terms? How many dimensions we have in that number of terms? It's the same thing, but for documents. So the number of dimensions is the number of documents, and each document is just represented by one in one specific dimension. But that's not what we learn, by the way. This is the input. What we learn as embeddings is again in this matrix. Okay? Documents. Yes, so the embeddings here are embeddings of documents, not terms. Say it again. We were inserting. Yes. Yes, exactly. A paragraph here means document. Yeah, it's just a name. Yeah. Yeah, you can say that each document here is a paragraph. Paragraph to vec is just the name of the method. Okay? Actually, we can. I mean, you can use this method and represent each paragraph. Yeah, Marina. Okay. Can you please? You can separate the paragraphs and consider them different documents. But in this case, if one document has 3 paragraphs, you will have embeddings for each of them. Maybe you can now average them. We can do so many tricks with this. Number of what? Tuba, don't confuse yourself with what a paragraph here is actually. Okay, it's just whatever we define. Okay, but it's not a term. That's the main point. It's more than one term. It can be a paragraph, can be a full document, it can be a window, anything that we want to learn embeddings for. Okay? By the way, these things you can train from scratch if you want. But there are pre-trained embeddings already available. Okay? But there is code also to train them from scratch. Maybe for some languages we don't have embeddings, so we can't train them. Or we have more data. We can retrain them. طيب. Okay, I will go through this slide, and doesn't seem that we have time for page rank. Which is in the homework. So, طيب, let me finish this slide first and then we talk about them. طيب, what we got so far, each term has one learned embeddings vector called word type embeddings. We learned one embeddings for each term, right? Right? You understand that? Okay. طيب, what is the problem with this? What is the problem with learning one embeddings for each term?
Exponentially complex.
One second, Muhammad. Yes? Between what? Why is it hard? I didn't get your point. Muhammad?
Would be exponentially complex because whenever we add a new term, we have to essentially find all possible pairings.
What do you mean by new term? The collection is already given, right?
Yeah, but the size of the terms of complexity, like whenever even between two collections, one extra term between two collections is exponentially harder than the other.
You mean if we have new documents, should we learn new embeddings? Is that what you?
Yes.
Theoretically, you shouldn't, unless the size of the collection, that you trained before was now very small relative to what we have before you retrain new embeddings. But, huh? Exactly. Okay, this is trained on very large, maybe number. It's not just one collection. It's many collections. But the problem here is different than what you mentioned. What? No. Look at this. Look at these sentences. Same word with different meanings. Okay, but yes. Okay, so what we learned is the word type. The word type is not the word token. It's the embeddings for the word type. We learned embeddings for the word bank. And that embeddings will, or that embeddings vector, represent all senses, all meanings of the word bank. But it might have been better to just learn embeddings for the tokens. So embeddings for bank here will be different from embeddings from bank here, will be different from embeddings from bank here. Okay? So the embeddings that we studied so far today are non-contextual. Okay, they don't depend on the current context of the word. And if I gave you a new sentence, if I give you a sentence and that I told you what is the embedding for that word in that sentence, it doesn't matter to you, right? Given what we studied, it's just a lookup table, right? We already learned the embeddings, so the embedding will not change by changing the context. Okay? Next, we want to learn something different. We want to learn different embeddings for different word tokens. So same word appearing in different contexts should have different embeddings because they might have different meanings. Okay? And in this example, it's very clear. Here, we're talking about riverbank. Here, we are talking about actual financial bank. And here, we're talking about blood bank. Okay? We need to have a method to learn contextual embeddings, which is, of course, I mean, that's the next generation of embeddings. What we learned today was kind of first generation, which is non-contextual. We were supposed to learn one method that is contextual embeddings, which is called ELMO. But we don't have time to do that. Yes. Exactly. It's not overlap. It will, all of them will lead to one vector. It's like the embeddings that we learned are a mix of the meanings of all of these. We didn't differentiate between different senses of the same word or the same term, right? If you think about it, if we give this sentences to the training model, it will learn one embeddings for bank that captures all of the context of that bank together. It will not give us these words. It will give us one vector that encodes all senses. Yes. Okay. So that was a shortcoming of or disadvantage of Word2Vec and its family. And there are methods to really learn embeddings given the context. Okay. If I gave the goal for these new models is that if I gave this sentence to the model and I ask for the embeddings of bank, it will give me embeddings vector. And if I gave it the second sentence, it will give me a different embeddings for the same word bank, just because that the context here is different. Exactly. It depends on its context.